Hi, everybody. I'm here to talk about a few more integral facts that you can get off of derivative facts, and we'll just work with some examples, how to find some nasty antiderivatives, thinking about them. But first, let me set my coffee up. All right, it's pouring my coffee. So in Calc 1, you learned about inverse trig functions. Like, for example, sine inverse of x. That's the angle whose sine is x, or tangent inverse x, the angle whose tangent is x, secant inverse x, the angle whose tangent is x. And you learned how to take their derivatives, and you found that the derivative of inverse sine of x is 1 over square root of 1 minus x squared, and you probably went, bleh. But you should really memorize this and use it, because now this is now an antiderivative fact. If you need to find the antiderivative of 1 over square root of 1 minus x squared, you could say, well, I know one antiderivative, inverse sine of x, just add on plus c, and I've got the whole family of antiderivatives that makes up that indefinite integral. Same way, you get 2 more indefinite integral facts for free. Now, you might say to yourself, hey, wait a minute, Dr. White, there are 6 trig functions, sine, cosine, tangent, secant, cosecant, cotangent. So there are 6 inverse trig functions, only talking about 3 of them here. What about stuff like, inverse cosine? Remember, the inverse cosine of x, its derivative was minus 1 over the square root of 1 minus x squared. Why didn't I talk about those, Dr. White? Well, the reason is, if you needed this indefinite integral, you could just take the minus sign outside using a property of indefinite integrals, and then use this fact here, and you would get minus the inverse sine of x plus c. Now, you could, if you wished, use this fact here, memorize it separately, and use it. But, I mean, it's just not needed. And, keep in mind also why they look so different. I mean, that looks different from this, but they're not really that different at all. If you look at a right triangle, and if you set up one side to be x like this, and you set up the hypotenuse to be a 1, then this angle right here is an angle whose sine is x. So I'm going to call it sine inverse x. And this angle right here, that would be an angle whose cosine is x, because cosine is adjacent over hypotenuse. And those two angles, they add up to 90 degrees because of the right angle taking up half the total 180 degrees in the triangle. And so inverse sine of x is actually the same as minus inverse cosine, just add on a constant, pi over 2. And so although there are 2 different approaches to finding the antiderivative, they're separated by a constant, so they yield the same indefinite integral. So just learn these 3, all righty? Another thing that's also useful, back in Calc 1, you learned how to take the derivative of any fixed base a to a variable power x. So an exponential with an arbitrary base instead of the usual base of e. And the derivative was a to the x times the log of a. Same thing times log of the base. So that leads to an idea for finding the indefinite integral of a to the x. Turns out it's going to be a to the x divided by the constant log a. Check it out. Take the derivative, and you'll see constant multiple rule for derivatives would give you a to the x as the derivative of this stuff. So you're going to want to remember this too. Here's just a tiny bit of practice. You can read the section 5.8 for more practice, and probably will have created a WebAssign around this as well. So let's try some practice. What if you need antiderivative of 4 over 4x squared plus 1 dx? Well, that looks tough, so let me procrastinate by getting my coffee. All right, I'm back. I didn't put things off very long. Well, I stare at this thing, this integrand, And it just vaguely reminds me of this. You know? That's how well you got to memorize your antiderivative formulas. They should just like pop into your mind when you see stuff that's structurally similar. And so I'm wondering if I could somehow bring this in to my problem here. And so I stare a little bit, instead of an x squared, I got a 4x squared. But you know what? 4x squared is quantity 2x squared. So why don't I just let u be equal to 2x in a substitution attempt here? Du would be 2dx, so dx would be du over 2. So let's try our substitution. 4x squared plus 1 would be a u squared plus 1. Here's my dx. And 4 over 2 makes a 2, which I take outside. And lo and behold, I now have the indefinite integral fact staring me in the face. This indefinite integral is going to be 2 times tangent inverse of u plus c. And so the answer to my problem is 2 tangent inverse of 2x plus c. What if I got this? Stare at it a while, and I've got a square root and my squaring, and then I take away a number. I've also got this like x hanging around outside. This vaguely reminds me of this, except there's no absolute value sign. So is there a way I could work it in? Oh, and before I go any further with that, let me point out that probably when you did Calc 1, when you found the antiderivative, you might have just thought of it as 1 over x times the square root of x minus 1. It turns out that the derivative is the same. The derivative is, if you consider negative values for a secant, which mathematically could happen depending on how you define secant, then mathematically it turns out that the derivative is the opposite of x times the square root of x minus 1. And so this is how they state the antiderivative formula. But in practice, when we use it, we can use it just fine when we see no absolute value sign. So anyway, I'm going to see if I can like modify this until it looks more like the derivative of secant inverse of something. So I want to see something squared here. I don't want to see 12 times it. I want to see a 1 here. I don't want to see 3. So I factor out a 3, and I just like move it over a little bit out. The square root of a product is the product of square roots. So now I've got that square root of 3 like factored out. And I look inside at what's here, and I'm almost in the x squared minus 1 pattern, but not quite. But I can use that same idea as last time. 4x squared is twice x squared. So I'm going to let u be 2x, du's 2dx, and so on. When I substitute back in, there's still going to be this x hanging around from back here. And that seems like a terrible problem, except since I let u be 2x, x is actually u over 2 all along. So the 1 over x could go to a 2 over u. I can take the 2 outside, and now I'm looking exactly at an integrand that is the derivative of secant inverse of u. So apply my indefinite integral fact, put the thing back in x's. I'm great. How about this one here? So that one looks vaguely like this one, the inverse sine fact. 1 minus something squared. So what can we do to make it look like exactly something squared? Well, if I let u be the square root of 5 times x, then u squared would be 5x squared. Root 5 times root 5 would make 5. X times x makes x squared. So I'm going to make that my substitution, which means when I get to dx, it's going to be du over root 5. So here I am substituting back in. And if I pull out that 1 over root 5, then I can just use my antiderivative fact just like before, put back into x's, and I'm great. How about this one? 5x over 1 plus x to the fourth. This looks like totally a stranger. But if you think about it, you know, if I were to let u be x squared squared makes x to the fourth. I could think of the x to the fourth as something squared. It's x squared squared. And then I would be looking at a 1 plus something squared on the bottom. And that reminds me of the tangent factor here. So could we recreate this? So let's let u be x squared, du is 2x dx, dx is du over 2x, do the substitution. The x's cancel. Yay. 5/2 constant can come outside. And now I can apply my antiderivative fact and put back in the x's. Let's try one with exponentials. Say I need the antiderivative of 9 to the x times sine of 9 to the x. Here it looks like 9 to the x is a candidate for an inside type of function. So let's let u be 9 to the x. du would be 9 to the x times log of 9 times dx. So we could get dx. And we can do our substitution. And all the x's cancel away and constants come outside. Antiderivative of sine is minus cosine, so I got a minus 1 over log 9 cosine u plus c. Put back in the x's. Great. That's enough examples for now. Plenty more in the book if you want to play around with them, but you definitely got 4 new indefinite integral facts that you want to be intimately familiar with so that those patterns occur to you when you see structurally similar functions that you've got to find an antiderivative for. That's about all I have today. See you again soon.